All right, welcome to The Explainer. Today, we're going to pull back the curtain on what feels like a magic trick your computer performs every single day. I mean, think about it. Right now, you might be writing an email, you've got music playing, maybe a dozen browser tabs open, and somehow it all just works. How does it do that? It feels like it's doing everything at once, but the secret is actually a lot more clever than that.
So, where does this magic start? Well, it all begins when we turn a simple, boring file on your computer into something alive, something active. And to really get how your computer juggles all these tasks, we've got to nail down the difference between the blueprint and the actual building.
Okay, so this is the absolute key distinction you need to get. A program, that's just a passive file. Think of it like a recipe just sitting in a cookbook. It's an exe file, a list of instructions on your disk, just waiting. But a process, that's when you're actually cooking the recipe. It's the program in action. It's running, it knows which instruction is next, and it has all its ingredients, its resources ready to go.
So, here's the takeaway. When you double-click that icon, you're not just running a program. What you're really doing is telling the operating system, hey, create a process for me. And that process is the fundamental thing, the basic unit of work that your OS has to deal with. And a process isn't just the code. When it gets loaded into memory, it gets its own entire workspace setup. You've got the code itself, sure, in what's called the text section. Then there's the data section for global variables. It gets a heap for memory it might need while it's running, and a stack for temporary stuff like function parameters. It's really the whole shebang, a complete package.
Right, so a process doesn't just get created and then sit there. Nope. It has this whole dynamic life, constantly moving from one state to another as it does its thing. So let's kind of follow it on its journey. See, as a process runs, what it's doing changes from moment to moment. We call this its state. And believe it or not, at any given instant, every single process running on your machine is in one of these 5 specific states. Okay, so its life starts as new. It's being created. Then it immediately moves to ready, which basically means it's standing in line waiting for its turn on the CPU. Then, bam, the scheduler picks it, and now it's running. Its code is actually executing. But hey, what if it needs to read a file? Then it goes into a waiting state until the file is ready. And once it's all done, it's terminated. And this whole cycle, it's happening for thousands of processes, thousands of times a second. It's nuts. Okay, so you've got maybe thousands of these processes all flipping between states like crazy. How on earth does the operating system keep track of it all without just losing its mind? I mean, it's a huge bookkeeping problem, right? Each process has its own priority, its own chunk of memory, its own idea of what it was doing last. The OS absolutely needs a system for this. And that system is this brilliant little thing called the Process Control Block, or PCB for short. Honestly, the best way to think of it is like an ID card for the process. Or maybe more like its passport, its driver's license, and its resume, all rolled into one. Every single process gets one. And inside this PCB is basically everything the OS could possibly need to know. What state is it in? Running? Waiting? What's the very next instruction it was about to execute? What were the values in all its CPU registers? What's its priority level? Does it have any files open? It's literally a perfect snapshot, the complete context of that process at any given instant. Okay, so now we know what a process is, and we know how the OS keeps tabs on it with the PCB. So let's get to the main event. How does the OS actually juggle all these processes with only a handful of CPUs? Well, this whole juggling act is called process scheduling, and the goal is incredibly simple. Keep the CPU as busy as possible all the time. The part of the operating system that does this, the process scheduler, its whole job is to look at that line of ready processes and decide, okay, you're next. And to keep things organized, the OS uses queues, literally just like waiting in line at the grocery store. The big one is the ready queue. That's the line for the CPU. But then you've got other lines called device queues, maybe one for the hard drive, one for the network. A process will bounce between these different queues its entire life. And it gets even cooler. There isn't just one scheduler. There are a few different types for different jobs. The one we've been talking about is the short-term scheduler, or the CPU scheduler. It's the one that has to be super fast, picking the next process every few milliseconds. But then you have a long-term scheduler. It's much slower, and its job is to decide which new programs to even let into the ready queue in the first place. And in between, you might have a medium-term scheduler that can temporarily move processes out of memory if things get too crowded.
Okay, we are so close to the final piece of the puzzle. We know the OS picks a process, but how does it actually make the switch from one to another so incredibly fast that it feels like they're running at the same time? This, my friends, is the secret sauce. It's a little thing called a context switch. This is the physical mechanism the CPU uses to stop working on process A and immediately start working on process B. It's that exact moment the juggler lets go of one ball to catch another one. So here's how it plays out step by step. Let's say process A is running along happily. Suddenly, an interrupt happens. Maybe its time is up. The OS instantly takes over. Step 2, it saves the entire state of process A, all its registers, where it was in the code, and stores it safely in process A's PCB. Step 3, it grabs the PCB for process B and loads its saved state into the CPU. And finally, step 4, process B starts running again, picking up exactly where it left off as if it was never even interrupted. But, and this is a really important but, there's a cost. During that tiny moment of the switch, the computer isn't doing any useful work for you. It's not running your browser or your music. It's just doing internal bookkeeping. We call this overhead. So, the faster the hardware can do that context switch, the more efficient the whole system is. Okay, so let's do a quick recap of the whole magic trick. We start with a passive program file, which becomes an active process. That process moves through 5 different states on its journey. The OS tracks every single one using that all-important ID card, the PCB. Schedulers are the traffic cops, deciding who gets to use the CPU. And the context switch? That's the lightning-fast move that creates the illusion of multitasking.
And that brings us to a really fascinating question, doesn't it? If every single switch has a cost, how does the OS make the perfect choice thousands of times a second to keep everything running smoothly? And what happens when all these separate processes actually need to, work together? Well, that's a whole other story, and it's exactly what we'll dive into in our next explainer. Thanks for joining me.